Dear friends, today we are taking the exercise of this chapter 1 standard 12. So we are taking the some exercise questions and we will solve this and we will check how the solution is this. So we are taking the first question 1.2. In this first question 1.2 question, two spheres are given and on each sphere the charge is kept. On the first sphere 0.4 microcoulomb positive charge is kept, and on the second sphere minus 0.8 microcoulomb charge is kept. So these two spheres are kept at the certain distance small r, and the force act between these two is given as a 0.2 Newton. So first question here is, what is distance between the two charges? That is the small r is equal to what? And second question, what is the force on the second sphere due to the first sphere? So here we are using the Coulomb's law to gain the answer. Here the medium is air between these two charges. So we will use the Coulomb's law. F is equal to k q1 q2 upon r square, where k is the proportionality constant and the value of the k is given by the 9 into 10 raised to 9 unit. So here we are using the equation F is equal to k q1 q2 upon r square. From that we get the equation r square is equal to k q1 q2 upon F. So here by putting the value of the k, q1, q2 and F, we get r square equal to 9 into 10 raised to 9 into 0.4 into 10 raised to minus 6 Coulomb into 0.8 into 10 raised to minus 6 Coulomb upon 0.2 Newton. So we get the r square 18 into 10 raised to 9 minus 6 into 0.8. So again r square is equal to 18 into 8 into 10 raised to 9 minus 6 minus 1 is equal to 9 into 16 into 10 raised to minus 4. So by taking the square root at both the sides, we get r is equal to under root 9 into 16 into 10 raised to minus 4 is equal to 3 into 4 into 10 raised to minus 2 meter is equal to 0.12 meter. So this is the first answer. Second answer, what is the force on the second sphere due to the first sphere? As here we are taking the Coulomb's law, and the force act on the first sphere due to the second sphere and the force act on the second sphere due to the first sphere are the same. So the force act on the second sphere due to the first sphere is equal to 0.2 Newton. So this is the second answer. Now we are taking the another question 1.6. Question number 1.6. In the question number 1.6, here 4 square corner points are given, A, B, C and D. On this square, the side of the square is 10 centimeter, it is 0.1 meter. So here on each corner the charge is kept. On the A there is 2 microcoulomb, on the B minus 5 microcoulomb, on the C plus 2 microcoulomb, and on the D there is a minus 5 microcoulomb. So here the charges are kept at the A, B, C and D corner of the square. The side of the square is 10 centimeter, and at the center of the square at the O point we are putting the 1 microcoulomb. So here the question is, what is the force act on the center of the square where 1 microcoulomb charge is kept? So here if we check the similarities, then we find in the square the distance from the corner to the center are equal for each corner. That is the OD is equal to OB is equal to OC is equal to OA. And here if we take the opposite corner, then at the opposite corner the charge is same. At the D point QD is minus 5 microcoulomb, at the B point QB is equal to minus 5 microcoulomb. and at the center there is a 1 microcoulomb, plus 1 microcoulomb. Same way, at the A point there is a plus 2 microcoulomb, at the C point plus 2 microcoulomb. So at the O point, the force exerted on the 1 microcoulomb at the O point due to the A and due to the C charge is opposite and equal forces. So FOD force and FOB force, they are equal and opposite force, and their resultant force is become 0. In the same way, FOD and FOA are also equal and opposite force, so their resultant force is become 0. So ultimately at the O point, at the 1 microcoulomb charge, the resultant force act on the 1 microcoulomb charge is given by FO is equal to FOA plus FOB plus FOC plus FOD. So it is 0 plus 0. FOD plus FOB is 0 plus FOA plus FOC is also 0. So it is the 0. So resultant force act on the O point, that means on the 1 microcoulomb charge, is become 0. So final answer is 0 force. That is the resultant force is 0. Now we are taking the another example. Example number 1.15. Now let us take the example 1.15. Here one uniform electric field in the x direction is given equal to 3 into 10 raised to 3 unit vector I Newton per Coulomb. Now there is one plane is given whose sides is 10 centimeter, square plane, and it is parallel to the YZ plane. So here the XYZ is drawn, and in the YZ plane the plane is parallel to the YZ. So it is given. So its area is become parallel to the electric field direction or in the electric field direction. So first question here is, what is the flux through the plane? So flux is given by the Gauss Theorem. Flux is equal to integration E dot dA is equal to sigma q upon epsilon 0. So we are using the equation flux is equal to E dot dA. So here E and dA, they are in the same direction. So angle theta is 0. So we can take here theta is equal to 0 between the E and dA. So cos 0 is equal to 1. So E dA cos 0 is equal to E dA, that is the 3 into 10 raised to 3 into dA. dA, that is the area. dA is equal to 10 into 10 centimeter square is equal to 0.1 into 0.1 meter square is equal to 0.01 meter square. So the final answer is E dA is equal to 3 into 10 raised to 3 into 0.01 is equal to 30 Newton meter square per Coulomb. Next question in this main question is, what is the flux through the same square if the normal to its plane makes a 60-degree angle with respect to x-axis? So here we can draw the diagram like this. In the xy, here the plane is like this. This is the plane whose direction, area direction, is making the angle 60 degree with the electric field or with the x-axis. So here we can get the area element which is parallel to the electric field direction or in the electric field direction, that is the dA cos 60. So flux is equal to E dot dA is equal to E dA cos 60 is equal to 3 10 raised to 3 into 0.01 into cos 60. Cos 60 equal to 1 by 2. So it is 3 into 10 raised to 3 into 0.01 into 1 by 2 is equal to 30 into 1 by 2, that is the 15 Newton meter square per Coulomb. This is the second answer. So here we get the flux 15 Newton meter square per Coulomb. So if you change the direction of the area of the plane like this. Then the flux, that means the number of electric field lines, are changed, either increase or the decrease. It depends on the angle chosen between the electric field and the area of the plane. Next question, question number 1.19. In this 1.19, what is the question given? A point charge of the 2 microcoulomb is at the center of a cubic Gaussian surface 9 cm on H. What is the net electric flux through the surface? So here one cube is given whose side is 9 cm, and at the center of this Gaussian cube there is a 2 microcoulomb charge is kept. So what is the total flux coming out from this cube, means from all the surface side? So we get the equation phi is equal to q upon epsilon 0, total charge enclosed by the Gaussian surface upon epsilon 0. So here we get value flux is equal to 2 into 10 raised to minus 6 coulomb upon 8.85 10 raised to minus 12. So flux is equal to 2 into 10 raised to 6 upon 8.85 is equal to 20 upon 8.85 into 10 raised to 5 is equal to 2.26 into 10 raised to 5 Newton meter square upon Coulomb. So this is the final answer of the flux, that flux is equal to 2.26 into 10 raised to 5 Newton meter square per Coulomb. So this is the answer of the question number 1.19. Now another example, we are taking another example 1.21. A conducting sphere of radius 10 cm has an unknown charge capital Q. If the electric field 20 cm from the center of the sphere is 1.5 into 10 raised to 3 Newton per Coulomb and points radially inward, then what is the net charge on the sphere? So here one rough figure is given. This is the conducting sphere. At the center we are taking the O point, and the radius of this sphere is 10 cm, and at the P point outside the sphere, the P point is 20 cm then from the center O. So at the 20 cm at the P point, the electric field is inward and having the 1.5 into 10 raised to 3 Newton per Coulomb value. So what is the charge on this sphere, that we have to find out. So here we are using the Gauss Theorem, and according to the Gauss Theorem, at the outside point P, electric field is given by Q upon 4 pi epsilon 0 small r square. Here small r is the 20 cm is equal to 0.2 meter. The electric field is 1.5 into 10 raised to 3 Newton per Coulomb, and Q is equal to question mark. So E equal to KQ upon R square. That means Q is equal to E R square upon K. Here K is the proportionality constant, and it is equal to 1 by 4 pi epsilon 0 is equal to 9 into 10 raised to 9 Newton meter square per Coulomb. This value we know very well. It is the known value. So Q is equal to E R square upon small k. That means Q is equal to 1.5 into 10 raised to 3 into 0.2 meter square upon 9 into 10 raised to 9. 20 centimeter is equal to 0.2 meter. We have to convert centimeter into the meter because electric field value is given in the MKS. So Q is equal to, by simplifying, we get 15 10 raised to 2 into 4 10 raised to minus 2 upon 9 10 raised to 9 is equal to 60 into 10 raised to minus 9 upon 9. So it is 20 by 3 into 10 raised to minus 9. 20 by 3 is equal to 6.666, approximately is written as the 6.67 into 10 raised to minus 9. So 10 raised to minus 9 Coulomb is the 1 nanocoulomb, we can write the answer 6.67 nano coulomb. So this is the answer. So dear friends, you can solve different examples given in the exercise. Here we have given the most of the questions related to all the topics in this exercise, and rest one you have to solve by yourself. And now from the next session we will start the second chapter, that is the electric potential and the capacitance. Okay, thank you.